Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Our mission today is a deep dive into forces that, often get ignored in basic structural analysis. We're talking about those sneaky culprits known as dynamic loadings and temperature stresses.
Yeah.
This isn't about the dead weight or static loads you learn about on day one. This is really the difference between a structure that holds up for a century and one that, well, fails spectacularly the moment you hit the ignition switch.
And these unseen stresses are absolutely vital for true mechanical integrity. The source material defines two critical categories we really need to master today.
Okay.
First, you have dynamic loading. This covers any situation where parts are not in static equilibrium. Think known acceleration or instantaneous impact.
In the second.
The second is temperature stresses or thermal stresses. They arise purely because we're preventing a material's natural response, its expansion or contraction, to a change in heat.
So today, we're going to pull back the curtain on this really ingenious engineering trick used to analyze known motion, the concept of inertia forces. We are going to find out definitively why a falling chimney breaks predictably at the 1/3 point.
A classic problem.
And then we'll tackle the catastrophic danger of resonance and dissect what happens when heat changes way too fast inside a thick-walled component.
All right, let's start with known motion. When something is accelerating, the forces are constantly changing. Calculating stress in a body that's always speeding up or slowing down, it's computationally really difficult, right?
Absolutely. The physics homework version of this is usually solved with a lot of calculus.
Right, but engineers found a much more elegant shortcut. If we know the acceleration, A, of every tiny particle in a body, we know the effective force is just the mass of that particle multiplied by A.
Okay, F equals ma.
Exactly. The engineering trick is to then apply an imaginary force that is equal and opposite to this effective force.
So you're neutralizing the motion. You essentially invent a counterload to bring the whole system back to, what, a conceptual rest.
Precisely. We call these inertia forces. By applying these imaginary forces, we can treat the entire dynamic system as if it were in static equilibrium.
Wow.
And now, all the internal stresses, what we call inertia stresses, can be calculated using much, much simpler static stress equations. It's a complete game changer for analyzing things like rockets, turbine blades, or any components undergoing rapid start-stop cycles.
Okay, let's see that concept in action with some simple geometry. Imagine a uniform rod being pulled in a straight line, parallel to its axis, with a constant acceleration. Where's the maximum stress?
It's right at the point of application, the loaded end. Every mass element in that rod is being pulled by the load, plus it has to pull the mass of all the elements ahead of it. So the total pull is greatest right at the start.
Now, compare that to the same rod rotating about one end with the uniform angular velocity, like a stiff propeller blade. The source material shows the maximum tensile inertia stress dramatically shifts. It moves to the pinned end.
And this is a crucial distinction. When translating, the stress is from an external force. When rotating, the stress is entirely internal. It's caused by inertia.
I see.
The inertia forces, which are pulling outwards because of the angular momentum, they integrate along the entire length. Therefore, the highest stress is right at the pivot, where the fixed end has to hold back the centrifugal force of the entire rotating mass.
And that maximum stress, how do we find it?
It's found to be proportional to the rod's weight, its length, and the square of its angular velocity. That quadratic relationship, that omega squared, that's the key warning sign.
And that leads us to some fantastic real-world examples of dynamic failures. The toppling chimney, for instance. We've all seen the footage where it snaps clean in two while falling.
But not at the base.
Exactly. Not at the base, but somewhere up the structure.
That failure point is not random at all. It's dictated by the physics of dynamic instability. If you model that toppling chimney as a slender rod swinging under gravity, the combination of its changing gravitational pull and the inertia forces, that's the structure resisting its own rotational acceleration.
Right.
It creates a maximum positive bending moment at a section located exactly 1/3 of the total length, L, from the pin base.
1/3 L. That is an incredibly specific and powerful piece of knowledge. It means any slender structure failing this way is likely to break right there.
Absolutely. And the same 1/3 L principle applies to earthquake loading. If you model an unanchored structure, like that chimney, and you impose a horizontal acceleration at the base, simulating a seismic shock, the maximum inertia bending moment caused by the structure's own mass resisting that sudden jerk is again located at 1/3 L from the base.
So the design takeaway is clear. You have to fortify the 1/3 L point just as much as the base itself.
You have to.
Let's talk high-speed machinery. Inertia forces become the dominant factor in things like turbine disks, where rotational speeds are just extreme. If we look at a solid, uniform disk spinning at some angular velocity omega, the tensile stresses, both radial and tangential, are equal, and they maximize right at the center.
And that maximum stress is proportional to the material density, the square of the rotational velocity, the square of the radius, and critically, a factor involving Poisson's ratio.
Right. Poisson's ratio, usually denoted, say, it describes how a material contracts in one direction when you stretch it in another.
Exactly. And in these complex stress calculations, it tells us how much the material wants to expand outwards tangentially when it's being pulled radially. It really influences the final maximum stress.
So if you double the speed of that disk, the stress quadruples because of that squared relationship. It really drives home why speed limits are absolute in rotational engineering.
And here's where the engineering complexity really kicks in. What happens if you introduce a central hole? This is an annular disk, a really common feature in turbine designs where you need a bore for a shaft.
Adams.
According to the source, the stress concentration shifts entirely. The maximum tangential stress no longer occurs at the center. Instead, it maximizes dramatically right at the perimeter of the hole, at the inner radius r0.
So that hole creates a discontinuity, forcing the stress lines to crowd around the edge. It becomes the critical failure point, the structural bottleneck.
Precisely. To make this tangible, the source provided an example of a conical steel disc rotating at 2,500 revolutions per minute, very, very fast. The combined dynamic forces plus external forces from attached turbine buckets and internal forces from a shrink fit were all calculated. The result showed the radial stress was about 6,020 pounds per square inch, but the tangential stress was more than double that 12,825 pounds per square inch. It just demonstrates that dynamic loading doesn't just increase stress. It creates a profoundly unequal and complicated state of stress that a static analysis would completely miss.
So we're transitioning from known acceleration to sudden transient forces impact and instantaneous loading. When you strike an elastic body, that force doesn't appear everywhere at once, does it? It generates a stress wave that travels through the material.
That's right. And that stress wave velocity v is an inherent property of the material. It's calculated as the square root of g times the modulus of elasticity E divided by the material's density delta.
So the stiffer the material and the lower its density, the faster that warning signal travels.
Correct. And for a simple longitudinal impact on an unsupported bar, the resulting stress E is proportional to the impact velocity E divided by the wave speed v, all multiplied by the modulus of elasticity E.
And what's fascinating there is that the initial stress is actually independent of the mass of the moving body itself.
It is, initially. It's only about the velocity and the material properties. However, in any real system, those waves reflect. If the bar is fixed at one end, the wave bounces back and combines with the advancing waves.
And that must dramatically increase the maximum stress.
It does. The maximum stress, max, then becomes highly dependent on mm, which is the ratio of the moving mass to the bar's own mass. You're suddenly dealing with compounding forces.
That complexity is why engineers often rely on a simplified rule for sudden loading, right? I mean, we often hear that if you instantly apply a dead load, so zero drop height, the resulting deformation and stress will be exactly double that of the static loading.
That factor of 2 is a standard, very conservative safety assumption used in design. But here's an interesting counterpoint from the deep dive material. The actual maximum stress from a sudden load is usually slightly less than twice the static stress.
Wait, hold on. If the actual physical stress is lower, I think the sources say it might be, 1.6, 3 times the static stress if the masses are equal. Why do we consistently design using the higher factor of 2? Why introduce that level of unnecessary conservatism?
You've just asked the critical engineering question. We use the factor of 2 because it provides a necessary safety margin. It accounts for imperfections, material variability, and the possibility that the load application isn't perfectly instantaneous, but maybe has some slight unknown velocity.
Oh, God.
It's a clean, simple, and most importantly, safe rule of thumb that ensures the structure can handle far more than the ideal calculation might suggest.
That makes perfect sense. Simplicity and safety outweigh absolute precision in a lot of design choices.
They have to.
Now let's look at periodic dynamic loading and vibration and its ultimate enemy, resonance.
Resonance is the synchronization point that structures just cannot survive. It occurs when the impulse frequency, F, of the external loads, say a rotating engine or traffic on a bridge, synchronizes with the natural frequency, F sub n, of the structure itself.
And when that synchronization happens without any damping, the theoretical amplification factor, the ratio of dynamic deflection to static deflection, it approaches infinity.
Exactly. The factor is 1 divided by the absolute value of 1 minus the ratio of F over F sub n squared. When the forcing frequency F gets close to the natural frequency F sub n, that denominator approaches 0, and the amplitude growth is just massive. It leads to excessive and usually catastrophic oscillations.
So the key for any engineer designing a bridge or a skyscraper is to calculate those natural frequencies first.
First, and make sure they are well outside any operational frequencies the structure will ever encounter.
Our sources provide detailed tables for calculating these. For instance, the fundamental frequency F1 for a simply supported uniform beam is proportional to the material stiffness. That's the modulus of elasticity E and the moment of inertia I. And it's inversely proportional to the beam's weight per unit length and the fourth power of its length L.
That fourth power of length is a huge factor. A
Yeah.
small increase in length leads to a massive drop in natural frequency. That's why long, slender structures are so much more susceptible to low-frequency vibrations and resonance. Knowing these values and the corresponding nodal points where vibration theoretically cancels out is just essential for designing structures that literally won't shake themselves apart. Okay, let's move on to the final category. Temperature stresses, or sigma T. These are the stresses that develop when a material's normal thermal expansion or contraction is physically stopped or prevented.
Right.
And we need to distinguish between two fundamentally different types of constraint here.
Type 1 being an external constraint, like fixing a component between two immovable walls.
Correct. The second, and often much trickier type, is internal constraint, where stress is generated purely by incompatible expansion within the body itself. Usually this is because of a non-uniform temperature distribution, or what we call a thermal gradient.
For external constraints, the simplest example is a bar fixed at both ends that undergoes a temperature increase, delta T. That temperature change wants to make the bar expand.
But the fixed ends prevent it.
Right. And that generates a compression stress that is proportional to the temperature change delta T, the coefficient of thermal expansion gamma, and the modulus of elasticity E.
And if you take that same concept and apply it to a fixed flat plate, the resulting compression stress is actually higher. It gets amplified by Poisson's ratio because now the plate is being constrained in 2 dimensions, not just one. The resistance to expansion is compounded.
Now let's look at the thermal gradient problem in a fixed rectangular bar. Say one face is suddenly much hotter than the other. The hot face wants to expand and the cold face doesn't, which causes the bar to try and curve, sort of like a banana.
If the ends are fixed, preventing that natural curvature, internal bending stress is created. The source material shows a maximum bending stress that's proportional to 1/2 delta T gamma E. And importantly, this is compression on the hot face and tension on the cold face. You've created a severe state of non-uniform stress purely through uneven heating.
And this leads directly to the danger of internal constraint, where no external fixtures are even needed. What happens when a surface is suddenly exposed to a heat source?
Well, if the surface of a solid body is suddenly heated by delta T, a massive compressive stress develops immediately in that surface layer. That surface layer wants to expand, but the stiff, cold core beneath it acts as an immovable boundary, internally constraining the expansion.
And that rapid surface compression, that's a primary cause of thermal shock.
It is. It's why things like ceramics or engine parts crack. Another example is heating only a small central circular spot on a disk. Within that heated area, you get internal radial and tangential compressive stresses. But immediately outside the heated spot, the tangential stress flips and becomes intensely tensile.
And that boundary between compression and tension creates maximum shear stress right at the edge of the heated zone.
That's where failure often initiates.
Finally, we have to look at transient thermal stress. This is where the temperature is changing over time, particularly in thick components where the heat flow kind of lags.
Consider a thick hollow cylinder, like a pressure vessel or a large pipe, where the outer surface is raised at a constant rate, say, degrees per second. Because the heat takes time to diffuse inward, The outer layer is always hotter than the inner layer.
So we have a constantly changing thermal gradient.
Exactly. And the complex formulas governing this, which depend heavily on the material's coefficient of thermal diffusivity, A, or how quickly heat equalizes, show that the hotter outer surface experiences compression, while the cooler inner surface experiences tension.
And that ongoing differential stress state during heat up or cool down?
It can be extremely destructive. It often leads to cracking that starts on the internal surface, right where that tensile stress is concentrated.
This has been a truly comprehensive look at the unseen mechanics of failure.
Indeed. I think our synthesis today is that mechanical integrity is determined not just by static loads and geometry, but by the material's intricate reaction to movement, which we measure by inertia, its reaction to speed, measured by impact waves and resonance, and its reaction to temperature fluctuations, measured by constraint. Ignore any of these, and the structure is compromised.
So everything we've covered, from high-speed turbine wheels to thick-walled cylinders, it all requires balancing inertia calculations, vibration damping, and precise thermal properties. Understanding these relationships, even if you don't memorize the exact variables, gives you the predictive toolkit you need to ensure longevity in any complex design.
And here is the final thought to mull over for your next design challenge. The sources noted a crucial scaling law for rotating systems. Geometrically similar rotating disks of different sizes will be equally stressed at corresponding points, provided they run at the same peripheral velocity. This raises an important question. In a world of increasingly miniature, high-speed components, how does prioritizing that peripheral velocity, rather than just rotational speed alone, force engineers to rethink and influence the ultimate physical size and design limits of systems exposed to these extreme dynamic and thermal stresses?